Hello and welcome to the Unit 5 Section 1 video on dilations and characteristics of similarity. So in the last unit we got a little bit of an introduction to triangles and how they work, and we also talked a little bit about relationships between triangles and congruence and things like that. But now we're going to talk about similarity. And with similarity, what we're talking about is figures that are the same shape but not necessarily the same size. So that's going to be our first definition here, is that of similarity. Okay, similarity are shapes that have the same shape, or figures that have the same shape but not necessarily the same size. So here 1 and 2, triangle 1 and triangle 2 are the same shape, but triangle 2 is just bigger than triangle 1. So therefore we can say that they are similar. They're not congruent because they're not the same size, but they are similar. Over here, triangle 1 and triangle 3 are not similar because not only are they not the same size, they're also not the same shape. Here we have an acute triangle. This one is a right triangle. So they are completely different shapes, so therefore they are not similar. So what is the definition of similar polygons? Well, they are two polygons are similar if and only if their corresponding angles are congruent and the measures of the corresponding sides are proportional. So this unit we're going to be talking a lot about ratios because that's how we're going to compare the sides. First, let's talk about the angles. So if we take a look at these two figures here, the angles all have congruence. That doesn't change, okay? So angle A is congruent to angle E. Angle B is congruent to angle F. Angle C is congruent to angle G. And angle D is congruent to angle H. So that part does not change. We're always going to be talking about congruency here when it comes to angles, because you have to have the same angles if they are to be the same shape. But if they are different sizes, then our sides are going to have different measures. And for them to hold the same shape, the comparison between the sides of the smaller figure and the larger figure have to be the same. That ratio has to be the same. So in other words, AB over EF has to be the same as BC over FG, and that has to be the same as CD over GH, and DA over HE. And in this figure, each one of those comparisons is the same. So if we do 6 over 12, we get 1/2. If we come over here and do 5 over 10, that's 1/2. 4 over 8 is 1/2. And then we have 5.4 over 10.8. Here we're dealing with decimals, but if you were to put it in your calculator, you would find it as 0.5. If you want to do it out long ways, just convert this to 54 over 108. Multiply both of these sides by 10 to remove the decimal, and 54 over 108 will reduce down to 1/2. So every comparison of the sides from one figure to the other is a ratio of 1/2. And that is what we call the similarity ratio. Now the similarity ratio is going to be different depending on if we're going from the small figure to the large figure or the large figure to the small figure. So if we were to go the other way and flip all these ratios, then our similarity ratio would be 2. But we'll get more into that as we go along. So let's talk about example 1. The triangles below are similar. We are already told that they are similar. So what we want to do is identify the pairs of congruent angles and the corresponding sides. And then we're going to write our similarity statement. Our similarity statement is triangle such and such is similar to triangle such and such. Okay, that is what a similarity statement is. You'll be asked to give similarity statements quite often in this unit. That's what a similarity statement is. So we have angle Z is congruent to angle R. That is indicated by the 1 tick mark on that angle. We also have 2 tick marks on Q and Y, so we can say angle Y is congruent to angle Q. Now, since two angles are congruent, two pairs of angles are congruent between these two triangles, then by default, the third angle must also be congruent. So angle X is congruent to angle S. Now let's compare the sides. We have XY over SQ. That's the first side we're going to compare. So XY is here, SQ is here. It's the side between our two ticks and no ticks. Okay, that's how we determine which sides we are comparing. We use the angles to help us out with that. So that is 6 over 9. And so therefore we have 2/3. Similarly, we pick the other sides and do our ratios there. YZ over QR. That's going to be 12 over 18, which is also 2/3. So it's looking good. We just have one more to check, and that is XZ over SR. And that is 9 over 13.5. You can turn that into 90 over 135, and that becomes 2/3 as well. Now, just like with congruence, when we write our similarity statement, we have to match up our vertices on our triangles. So triangle RQS is similar to triangle. Now let's take a look. We've got 1, 2, and none. So 1, 2, and none. Z, Y, X. All right, let's try this again with B. First, we'll take care of the angles. Well, the obvious one, first of all, is the 90-degree angle. Angle B is congruent to angle G. Then we've got the one that is indicated for us, the 59-degree angle. So angle C is going to be congruent to angle H. And then by default, the last angle has to be congruent. Angle A is congruent to angle J. So now let's compare the sides. We're going to start with AB to JG. That ratio is 10 over 5, which is 2. Then BC to GH. That ratio is 6 to 3, which is also 2. And then AC to JH, that's 11.6 over 5.8. Again, if you move the decimal and make it 116 over 58, you can reduce that down to 2 as well. Likewise, if you put 11.6 divided by 5.8 in your calculator, you're going to get 2 anyway. And so, triangle ABC, again, matching up your angles, your vertices, is similar to JGH. So now that we've discussed what similar polygons are all about, let's see what we can do about identifying similar polygons. So a similarity ratio, I've already kind of mentioned that. A similarity ratio is a ratio of the lengths of the corresponding sides. Okay? So similarity ratio is the ratio of the lengths of the corresponding sides of two similar polygons. So in this example here, you've got the similarity ratio of ABC to DEF, so going from the small to the large one is 3 to 6, or 1/2. The similarity ratio DEF to ABC is 6 to 3, or 2. Okay? So let's take a look at example 2. And we're going to determine if they are similar, and if so, we're going to write a similarity ratio and a similarity statement. So first of all, these are rectangles, and we know that all of the vertices or all the angles in these rectangles are congruent because they're all 90 degrees. So let's go ahead and go straight to the sides. Well, we only have two sides to check because the top one's 12, that means the bottom one's 12. The one on the left is 4, so the one on the right is 4. So we only need to check the top one and the left one because we've already checked it. It would look exactly the same for the other two sides. So let's start with the top one. PQ to TU is going to equal 12 over 16, and that reduces to 3/4. Okay, now let's check the other one. PS to TW. Well, that's going to be 4 over 6, which that reduces to 2/3. So our ratios are different, which means that the corresponding sides are not proportional, and the rectangles are not similar. Let's try these two triangles. Now here, we know that angle A is congruent to D, angle B is congruent to angle E, and so by default the third is congruent. So we have that, okay? Now let's check the sides. So we'll start with AB, and we're going to compare that to DE. So that gives us 20 over 15, which is 4/3. Now if we do BC over EF, that gives us 24 over 18, and that is also 4/3 when you reduce it. And then finally AC over DF is 16/12, and that is also 4/3. So all of our sides have the same similarity ratio. So the similarity ratio is 4/3, and our similarity statement, triangle ABC, is similar to triangle DEF. Remember, you have to match up those angles just like you did with congruence. All right, all this is all well and good, but we really need to apply some of these concepts. So let's take a look at a rail boxcar and talk about making a model, or actually using a model to determine the size of the real thing. So what you're being shown here is the dimensions of a model, 2 inches by 7 inches. If the length of the actual boxcar is 50 feet, we want to find the width of the actual boxcar. So we're going to let X be the width of the actual boxcar. Now we are going to use a similarity ratio to achieve finding out what that width is. The rectangular model of the boxcar is similar to the rectangular boxcar, the real thing. So the corresponding lengths will be proportional. So we're going to have the length of the boxcar over the width of, or actually over the length of the model. Okay, we're comparing that similar side, okay? And we're going to compare that, or set that equal to the width of the boxcar. Again, talking about the real thing here, and we will have the ratio be to the width of the model. Okay? So, the length of the boxcar, we are told, is 50 feet. The length of the model is 7 inches. The width of the boxcar is what we're trying to find, and the width of the model is 2 inches. So from here, you're going to cross multiply. 7 times x is 7x. 2 times 50 is 100. And then divide each side by 7, and you're going to get that the width of the boxcar is approximately 14.3. Now again, we have to use units here, okay? So we are going to sum this up with a quick little sentence, because this is a word problem. The width of the boxcar is approximately 14.3 feet. The last topic for this section is drawing and describing dilations. So here we're talking about transformations. And if you remember in the last unit, we talked about rigid transformations. And those were transformations that we move the figure around, we flip it, we reflect it, we rotate it, but the object itself doesn't change. Two of those objects are going to remain congruent. The original object and the transformed objects would be congruent. Well, now we're going to talk about dilations, which is when the model or the figure shrinks or grows. Now, the transformation that maps xy, and we're talking about a set of coordinates for a point, so point xy, this is going to be one of the corners of your polygon or one of the vertices of your triangle. If we're going to map it to kx, ky, where k is greater than 0, this is a dilation. And it is a dilation with, and actually let me spell it right, it's dilation, no A there, dilation with center 0, 0. So we're dilating about the origin. Okay, the origin is kind of our center of dilation. And a scale factor of k. K is our scale factor. If k is between 0 and 1, then the dilation is a reduction. So your figure is going to shrink. If k is greater than 1, then your dilation is an enlargement. Your figure is going to grow. Of course, if k equals 1, then you're not growing or shrinking, so therefore you have no dilation if k is 1. So in a dilation, the image and pre-image are similar because they have the same shape. When figures in a dilation are polygons, the image and pre-image are similar polygons, so the corresponding side lengths are proportional and the corresponding angles are congruent. In other words, dilations preserve angle measure, which is exactly what we were talking about with similarity in this section. A transformation that produces similar figures is a similarity transformation. You can tell that we are not that clever in how we name things. We just call them what they are. And a similarity transformation consists of a dilation alone or a dilation combined with either a translation, a reflection, and or a rotation. Because remember, those are rigid transformations and do not change the shape. Two figures are similar if and only if there is a similarity transformation that maps one figure to another figure. So let's do a couple of examples of this to wrap up the unit, or wrap up the section of the unit. So in example 4, we're going to apply the dilation D to the polygon with the given vertices, and then we'll describe the dilation. So here we have coordinates. If you can find your coordinates, then you can easily dilate it. So we're going to dilate it by a factor of 2. So that is what our scale factor is. So we are going to go to A prime. A prime is what we're going to call our dilated figure. So 2 times 2 gives us 4. 2 times 1 gives us 2. For B prime, 2 times 2 is 4. 3 times 2 is 6. And for C prime, 2 times 5 is 10. 2 times 1 is 2. So we're going to plot these coordinates. So 4, 2 is here. That's going to be my A prime. 4, 6 is here. That's going to be my B prime. And then C prime is going to be at 10, 2. And then from here, we're just going to connect our lines. So we have B to A here, A to C here, and C to B here. And so this is our dilated figure. Now let's describe the transformation. It is a dilation. So here's our description. This is a dilation with center 0, 0 and scale factor 2. All right, example 5. Now we have a scale factor that is 2/3, but we do it exactly the same way. Do not let the fraction discourage you. So let's start with P prime. -6 times 2/3. 6 divided by 3 is 2. 2 times 2 is 4, so we have -4. 3 divided by 3 is 1. 1 times 2 is 2. So that's our P prime. Q prime is going to be 3 divided by 3 is 1. 1 times 2 is 2, so I got -2 here. 9 divided by 3 is 3. 3 times 2 is 6. And then for R prime, 3 divided by 3 is 1. 1 times 2 is 2. 6 divided by 3 is 2. 2 times 2 is 4. So these are our ordered pairs for our new figure. So we'll plot those first. -4, 2 is here. -2, 6 is here. And 2, 4 is here. And let's label them. This is P prime, this is Q prime, and this is R prime. Now all that's left to do here in the graph is to draw our lines to connect our sides, or our vertices to create our sides. And you notice that the figure is smaller, and that would make sense because we have a dilation factor of less than 1. So to describe it, this is a dilation with center 0, 0 and scale factor 2/3. And that's it for the section. Coming up in the next section, we're going to talk about proofs of similar triangles. Just like we had congruent statements like side, 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 and side, angle, side, and angle, angle, side, we have similarity statements that we can make to show that two triangles are similar. So we'll be talking about that in the next section.